I definitely don't suggest getting all motivated like you would here. Don't suggest getting all motivated and be like, I'm gonna read it before the end of the day, because you'll forget it. You know, you want to progressively read and then end, you know, the week before school, or the week that school starts. So.
I like burning my brain if I read it.
And you don't want to cram it, you know, all in. So I'm gonna sit over here in this middle, I guess. Dun, dun, dun.
You ready? No.
I know. Now keep in mind as we ask the questions, you know, talk a little bit before Ryan came. You know, we're not looking for perfection. We always have to refine our answers and our thinking about you know, topics and how we respond to students. You know, there are some fairly standard things that they will ask in ways that we should respond. So I'm not looking for, you know, perfection, a clear, you know, perfectly clear and concise. Just at this point in the game, with what you know, what would you say? What would you do? You've got, you know, 3 minutes for a problem, you know, to say, or for a question. What are you going to say? And it may be very well that you can do something in 30 seconds, you know, to say, you know, to answer it. Maybe the deriving the quadratic formula. You know, will you be able to derive it? If somebody gets that, you don't necessarily have to derive it all, but where does it come from? Start out and say, okay, well, if you do this, and then I'll start it out for you. Let's not do all the, you know, tedious algebra in there, because you do tend to make a mistake when you start doing all that with the A's, B's, and C's. But can you tell us, you know, where does it come from? So don't think, oh, I have to, you know, derive it perfectly cold, you know, too. Because if you were preparing a lesson and you were going to derive the quadratic formula, you would spend some time, right, figuring it out. You'd have your notes, and you'd say, but you should be able to answer, like, well, where does it come from? You know, tell the kid a little bit about where it comes from. So the first one is this. You might even be able to sit for this, okay? You might even sit for this one. So, oh,
this is first name, right?
Yes, Ashley.
Okay.
Yeah. So it's Ashley, Cody.
Your last no matter what.
Yeah, exactly. You got.
Unless
right?
it's reversed.
Yeah, well, that's true. It's Ashley, Cody, Jess, and then Ryan. So that's how it would be. And whether Jess's name's Jess, Jen, or Jessifer, you know, they all start with a J, and so she is third. So Ashley, the question is, what does it mean to examine secondary school content from an advanced perspective? So what did you learn in the class about, like, we're trying to examine secondary school content, but do it from, you know, a little bit of an advanced perspective. What does that mean?
Well, I learned that if you examine like math ideas more and like in depth, then you get a deeper understanding of your content, and then you can relay that to the students in the classrooms. That way they have a better idea of what they're learning.
Okay, so, there could be follow-up questions too, but, no. So examining it in depth, what does that entail? Like, how do we examine something in depth?
Well, you do more research, and then you also can look at the proofs as to why things are derived and where they come from, and then also how they work in real life situations as well.
Okay, all right. And I will add something to that too. Real life situations, but also connections, you know, connections with real life, but connections within math. How are these things related, so on and so forth. So, yeah. All right, good. Cody. That one wasn't too bad, was it?
No, that was an easy one.
I know. And I'm not putting, this is not choosing with your
Oh, okay.
Wait, why not? I like that one.
We did start out with the easy. The guinea pig. The guinea pig.
I thought the odds would get better since I was last, but apparently they're getting worse. Give them away.
Some of these are like all tied together.
So I don't know.
Okay, ready? Cody gets this question. Oh, and again, you have the board, so some of these you might need to.
That means I have to
You don't have to. So what does it mean? I read this in a book. I read this in my notes, Cody. What does it mean that a quadratic function has a constant second
okay.
difference.
That was my
You
favorite.
scared me there. I was like, yes, it's the heart.
What does it mean?
my
Quadratic, we all know what a quadratic function is. What does it mean as a constant second
Well, I
difference?
don't even need the board for this, really. The
Well, showing something is always good.
Okay,
but
well, I'll show it then.
you can
So,
practice writing on the
the constant differences are, like, the first constant difference would mean that for a first power polynomial, like, the differences are the first, how do I say this?
Well, show us an example. When you're struggling to say something, putting something on the board, you say first. Well, I don't know what you said, first degree or whatever.
So,
but we're talking function.
Yeah, first degree. That's what I meant.
So that's a linear, right?
Yeah, this one would just be linear, and then for your x is equal to 1, 2, 3, 4. Just do 4. You would have 4. 4, 5, 6, 7. So the difference between these would be the first difference, and it's just 1 for each of them. Well,
Okay.
but then if you were to take a quadratic of, just do a simple one. I believe one used in my book was like this. Your values come out to be 4, 7, 9, 12, 18. So the first difference between them, you get differing values. But then the second difference from those ones would be a constant second difference of just 2 between each one. And then the same holds true for cubics, but it would be the third difference.
Alright. Good. Okay. No follow-ups. Wait, so yeah, here's my follow-up. So if it was a cubic equation, which difference would be constant?
The third one.
You said 4.
Wait, oh, okay.
Well, it wasn't her question, so she has the right to.
Yeah, she was trying to sabotage. Alright, Jess.
That was like a longer question than
Jess. Oh, nice. Okay.
Oh, no.
One of my favorites.
Oh,
One of my-
is it 3 axioms?
No, that's too easy. That's in there, but it's too easy.
That's too easy.
What does the arithmetic average mean as a balancing point?
Oh, it
You
means.
can explain it, but then I'd like to see a little example too. But yeah, you can explain it. I'd love to hear this in words. What is it? Because I think we should. For instance, Cody, you ought to be able to say, well, when you find the difference between values, and this is a little bit more difficult, I think. When you find the difference between values in a quadratic, it's not constant. But if you find the difference between those differences, the second difference, then it is constant. But I really need an example there. For Jess's question, what's the arithmetic average mean as a balancing point? Probably ought to be able to describe that somehow in words, but then showing an example would certainly help us. So, all right, what is it? What's balance, or what's arithmetic average as a balance point? But it certainly help having an example first.
Yeah, probably.
So whatever you want to do. That's totally key.
Okay, I'm just gonna go
When
read.
Steve said the words quadratic, my heart stopped.
Yeah.
You thought you were
I'm
gonna.
trying to think of
Might
something
be
really
an
easy.
increase for you.
So, I guess if you have.
Yeah. Now, okay. So you're probably trying to think of an example that's going to come out nice.
Yeah.
Probably not going to be able to do that until or you're probably not going to do that unless you were sitting in your office saying, okay, I'm creating a lesson to do it. So since you don't have that luxury of spending 10 minutes to do that, let's just throw some numbers out there. So don't feel like you have to really struggle up there to say, well, what would make it really easy? Because you might not be able to do that. So let me just throw some numbers out there, and let's say, what's that?
I can throw some that are pretty easy.
Okay, go ahead. Do you have how many?
4,
Okay, go with 4.
8, 10, 14, 16.
Okay, but I also would want to make sure.
They're not equal. There's some.
Yeah,
Because mine are a symmetrical example.
yeah.
Okay.
So that would be the problem, you see what I'm saying? So, but that's okay, let's go 3, but it is nice to have like 4 of them, you know what I'm saying?
Yeah.
So, let's say 3, 5, 8, 20. Now, hold on, let me think for a second. See now, I'll tell you what I'm doing is this. I'm saying 28 and 8 is 36. 36 divided by 4, so I do get a nice number, right? 30, what did I say, 36?
Yeah.
36 divided by 4 is 9. So I do know that my average is a whole number, okay? So maybe above it, say x bar equals 9. Because if it wasn't, if I would have gotten a sum there of 37, I would have said, well, there's 4 numbers, so let me subtract 1 from one of them or add whatever. But and then I'm also looking at those numbers and I'm saying 9. Do I want to give it away? No, I'm not going to say anything else about 9 right now. So x bar is 9. So what does it mean that 9 is a balancing point for these numbers?
Can I put it like on here then?
Sure. And now you
I'll
do
put it
whatever
in
you
my
want.
color.
I probably should have given an example here, but yeah, it's all right. Okay.
So when it means that's a balancing point, I'll see now I don't even. So between 3 and 5, you have 2 as your distance, and then between 3. 3 and 9. No, wait, hold on a second.
Yeah, and that's all right. You don't
Am I right when I do that?
Well, I want you to continue thinking because sometimes you're not even teaching average, and a kid comes in and says, "I read this someplace because we have the internet, and I read this balance point, and I really didn't understand what they mean." Well, I haven't taught that in a while, and I have to think. And I might start initially saying, well, if you look at the difference between 3 and 5, and then I have to determine, wait, is that really what I mean? I mean, it's possible I might say, let me go home and come up with a good example, blah, blah, blah. Right now, you don't have that luxury. So keep thinking about what you're doing there. You said 3, 5 is 2. Then you start to say 3 and 9. So keep in mind that the average, which is 9, is the balancing point. That might be a little hint.
So that'd be 5 to 9 is 4.
Okay, so do something with that. How you gonna write that? 5, 9. That's 4.
And then 8 to 9 is 1.
Okay.
And then 9 to 20
Okay.
is 11.
Okay. Now, I want you to look carefully at the very first thing you did. From 3 to 5 is 2. How is that? Which one of these is different than the other?
The 3 needs to go to 9.
Okay. Right. One of these is not like the other.
And 3 to 9 is 6.
Okay.
So then, I guess I don't know where to write this. So the 3 to the 9, which is 6, plus the 4 from the 5 to the 9 is supposed to be equidistant or equal to the distance from 8 to 9, which is 1, plus the distance from 9 to 20, which is 11.
Which isn't. Right? 10's not equal to 12.
Yeah.
So,
Oh, it's because of the. Wait, no.
now this is exactly the, no, you're doing fine. This is exactly the reason why I made the average be 3 on the left and 1 on the right. Okay? Because I wanted to prove a point that is not proven if I stick it 2 and 2. Now I could have done the easy thing and made there be 5 numbers, and then of course it has to be 3 on the one side and 2 on the other.
Mhm.
Alright? But you are focused on there being 4 numbers, 2 higher, 2 lower. not the case. It's 3 lower, 1 higher. So 6 plus 4 should not just be 6 plus 4. Think about it. How are you going to make these numbers equal? What are you going to do?
You gotta put the 1 on this side from the.
And doesn't that make sense? Because isn't the 8 on the same side as the 3 and the 5? You see that, Jess?
Yeah.
Okay.
That makes more sense.
And is that, okay?
Yeah.
All right, so those are equal. So you've shown us that it's a balancing point. Now say something to us. That 9 is a balancing point with respect to what?
With respect to the distance from the data values on the left side to the right side.
Right, and let's maybe even say it's the balancing point with respect to the sum of the distances, right?
Oh, yeah.
You know, to maybe clarify it even more. The sum of the differences. So you add distances. I mean, I guess it's still differences, right? You add the distance that 3 is from 9 to the distance that 5 is from 9 to the distance that 8 is from 9, because those are the ones on the left side, lower than it. And then the balancing point means that that distance is the same as the distance that 20 is from 9 on the other side.
Yeah.
My follow-up question, though, is how is that different than the median, not the mean, not the arithmetic average, but the median also being a balancing point? What does the median balance?
The median is like the amount of numbers on the right side. Well, not like adding them,
Yeah.
but how many numbers
How-
are
right.
on the right side to the left side.
Right. How many are on the right versus how many are on the left? Okay, good, okay. Right, my hard one. Not that I have any control over
I
this.
mean,
It's a good idea.
I was late, so I gave myself an A minus.
On that part, we're being late this time?
Yeah, and I wrote today.
All right, are you ready?
I
What
guess.
is the pattern to show students for why a to the 0 equals 1 when a doesn't equal 0?
When A doesn't equal
When A
zero.
doesn't, yeah, I mean,
that
that
throws
just-
me off.
Yeah, that clarified. I mean,
Yeah.
honestly, for kids,
That's
I probably wouldn't focus on that. I would mention it.
That's
in
an
the-
example where it's always 0. So.
Yeah. Well, no, that's the one where we're not sure if it's
Oh,
0
yeah,
or 1.
Yeah.
And so
I
you
was saying
say-
0.
Yeah, you say that we
First,
just don't
second,
determine.
yeah.
Yeah. So you are asked what is the pattern to show students for why a to the 0 equals 1. So maybe put a to the 0 equals 1.
Yeah, right.
So I don't understand, Mr. McMahon, why a to the 0 equals 1, which is why, think about what that's saying, why anything that's not 0
Yeah.
to the 0 is 1. How do you start? What do you do?
Well, I'd like to start by saying,
No,
by looking at a couple of things, such as 3 squared equals 9, 3 cubed equals 27, and 3 4 equals 81. I'm not going to show you the pattern immediately, because I think that a lot of people should not just understand why anything to the 0 power is 0, but more or less show that the base, what these are, which then you can see, oh, anything to 0 is 1. So 3 squared means this is the power. So you have to think of, what does the power mean? 3 squared is 9. So whenever you now think of the number 9. If you take 9 divided by 9, you surely get 1. Do that with 3 cubed, 27, divided by 27. 3 to the 4th, 81, divided by 81, you'll always get 1. Now, that doesn't show you the pattern, which I will do now, but I feel like that has some merit in the reasoning. So without further ado, we shall show you the pattern.
I would expect
I'm gonna
that.
miss him in methods next time.
Yeah.
I'll start with the ones we know, and I'll show you it. There is a pattern here with the power, and the pattern here is from 81 to 27, you are dividing by 3.
So now that's just the right side. There's also a left side to it. And the pattern here is that the exponent,
He's just making sure that he is.
is lowered by 1.
He's answering 2 questions.
Yeah.
So let's continue this pattern. Divide by 3, subtract 1 from the exponent.
Which the note, somebody might argue with that notation on the left, but he is explaining
And
what
now,
he means negative.
without further ado, the long and behold question that half of you might not even be able to see.
3 to the 6.
3 to the 6. My hands have... I'm gonna need a class on writing it on the board afterwards, by the way. Drawing circles is hard. Divided by 3, subtract 1. 1 minus 1 is 0, and 3 divided by 3 is 1, which shows you that 3 to the 0 is 1. And if you were to continue the pattern, this is also why any exponent 3 to the negative 2 would equal 1 over 9. Because you could then continue this trend and say minus 1, oh, that's 1/3. And divide, because you're dividing by 3 again, do it again to get 1 over 9. So that's a bit extra.
But Mr. McMahon, that only shows me that 3 to the 0 is 1. The question is, how does that explain why a to the 0 is 1?
Very, very good, Steve, and my ignorance has shown that I have only done for one number. Without further ado, I shall now do in the general.
We need to buy him a compass so that we can use.
Alright, so a to the 4th. What does it mean to say a to the 4th? Of course, I'm explaining it. You shouldn't be answering.
I'm just gonna answer rhetorical.
You take...
This isn't a lesson, right?
This is the part where I screw up, too. Where you take
That's why he asked us the question.
You take the base here, A. How many times do we use the base as a factor? Thank you, Steve,
We're all
for helping me out.
Yeah.
So, is a factor a to the 4th, the power, is equal to a times a times a times a. Now let's go a to the cube. What does a to the cube have? Well, it's a times a times a. Wait, but there's not 4 a's, there's only 3. 3 right there. So there's a trend here as well, as you can see. The same trend is over there too, where you subtract 1. And here, the trend, while it looks a bit different, it still is the same. Don't get me wrong. Well, you really can't see it because this thing, let me tell you how much money this thing's worth to me, is divided by A. So instead of A here, you can have 3, you can have 5, you can have 1, you can't have 0 though, as explained earlier. So let's continue this pattern. A times A.
We have to work on his conciseness.
Divided by A. Oh yeah, I'm going over. I'm getting like a 0 for how long it took me. I just want to do for completeness have all these little minus ones because that's important to show this trend, even though you already saw it over there, unless you couldn't see it. But as the trend goes, you subtract 1 from the exponent until you get to 0. Which is still a 6, and you get these 4 a's will go down to 3 a's, will go down to 2 a's, will go down to 1 a, which will go down to 1. Because a by a is 1, not 0.
Okay.
I have chalk and paper ink on my hands now.
Now, possibly I would show 3 and then 4. You could also say 3 and then 4.
Yeah.
Several things. So
I just wanted
why don't
to
you erase that?
Oh yeah.
Coach, you go up and erase yours. All right, back to Ashley.
Oh, we're doing more than one question?
Yeah.
Oh, let's
What the
go.
heck, man? I got 20
Thanks to
questions
the
in here.
record.
Crazy, we're gonna keep going until we can't go
I have
anymore.
a 1 in 4 chance of getting a quadratic formula unless...
You know, 1 and done? Jeez. We're not 1 and done.
Thanks to the rain.
Ah, okay. Yeah. Oh, I still had till 11:30. I didn't have to leave till 11:30. Ashley. Where does the plus minus come from when solving x squared equals 16 by taking the square root of both sides and getting x equals plus minus 4 for the solution set?
Well, you invoke.
So why don't you go up there and write down x squared
Don't
equals
speak,
16.
just write.
Well, you know you can speak too, but I want you to write down x squared equals 16. So start there, and we know the answer is x equals plus minus 4. Where's the plus minus come from? Alright.
So, you're basically invoking the square root principle without showing it. The missing steps is if you're going to solve it by, showing everything worked out. You would start out with x squared equals 16, and then you take the square root of both sides. So you have the square root of x squared equals the square root of 16. And people think that the square root of x squared equals x, but it actually equals the absolute value of x. And the square root of 16 is 4. When you take the absolute value of x equals 4, then you get the plus and minus 4 for the positive and negative values.
So the plus minus really comes from the distance, which is absolute value, right?
Yes.
It's the definition of distance, not the definition of the square root of x squared, being x.
Mm-hmm.
Okay.
Yeah, so those are like the missing steps that people forget.
All right. So notice what she said. Her explanation would certainly assume that we have already talked about the square root principle, right? Because she said, well, you're invoking the square root principle. Well, as a teacher, then teach the square root principle. What does it say? Whether you prove it or not, it doesn't really matter. I mean, I think you should, but it doesn't really matter if you prove the square root principle, which is exactly what she's done over here. It just
Yeah, you
with a
can say
specific
like
one.
by definition of the square root.
Right. So you're just invoking the square root principle, saying that if x squared equals 16, then x equals plus minus 4. How's that square root principle proved? It's proved because the square root of x squared is the absolute value of x, so you can put it over there as well. Good, okay. Alright, 5 done. Woo!
I know, I was gonna use
Actually, I thought it was a bit harder than your last one.
Sort of. Yeah. Alright, go, Cody. Oh, Cody has an easy one, maybe. Why is 36 called a perfect square, Cody?
Because if you were to take 36 objects and create rectangles of these 36 objects in different dimensions, you would be able to, 36 is one of the numbers you would be able to make a special rectangle known as a square.
Good. Alright, you didn't need an example of that one, right?
I would
But you could
have
say-
taken 5 minutes.
I know exactly.
27, drawn 36. I already drew 38 too.
Yeah, exactly. Well, that makes for a good lesson. The quick explanation,
Oh yeah, this is our quick explanation.
Yeah.
Sure, next those up, see.
Let's see. Oh, another one of my favorites.
Three axes?
You really just want that theory. Yes, what are the 3 axes? Why does the elimination method work when solving systems of equations?
Oh, because you're just making equivalent equations on both sides.
Okay, by doing what though? So a visual is probably a little better here. So if you had a system of equations, so for instance, I'll just say, 2x plus 3y equals 8. And then 5x minus 3y equals -2. So the elimination method says just add them together. So you're saying you're making equivalent equations, like by doing what? Explain, like what do you mean? How are we making equivalent equations? So why don't you put a plus sign, kind of between them over here to the left, like you would normally do, like plus, and then draw a line. And we know that we would normally just add them together,
And then you get
right? And what would you get?
the 7x equals, oh, that's a -2, hold on. So that would be 6. And then you
So
would,
why is it okay to add those 2 equations together?
because, like, if you just took the 2x plus 3y equals 8, if you add, like, if I took 2x plus 3y and added 2 to this side, and then I did the same on the other side, these are still equivalent to each other.
And equivalent
size-
means they have what?
They
The same.
values.
I'm not saying, well, the same value. I'm trying to think. Let me see if that's. No, I don't want to say same value because it's this equation is equivalent to this equation. It means they have the same solution set.
Oh yeah.
Okay? It means the numbers that make this equation true are the same as the ones that make this equation true. Okay? Alright, so you're saying that when you add 2 to both sides, you make equivalent equations. Okay, keep going.
And then
What's that have to do with this over here then? And you could just directly, well, you could just directly go over to this and probably explain why, unless you want to go through some progression. But why are you saying, because your quick answer was, you're just creating equivalent equations. I buy that as an answer, but it needs further explanation. What do you mean? So you started us out saying, if you added 2 to both sides of that first, you make an equivalent equation, continue.
Okay, so then if you would take your 2x plus 3y over here. Oh my gosh, I can't even write today.
Same.
2x plus 3y, and then if you would add this, which is the plus 5x. Oh my gosh, I'm looking at it. Hold on. Let's go back. I was gonna do down here. So 2x plus 3y. And then you add the 5x minus 3y. And then you come over to this side and you get 8 minus 2.
Let's
Then-
put plus a -2 on that. You actually probably would have had enough room on that because you were really on the right side only going to do 8 plus a -2. All right, what does that have? How is that making equivalent equation? So you do get what? When you do that, if you want to simplify it, you get 7x equals 6. Okay? So explain why that is the same thing as up there where you added 2 to both sides. See on your right side? You
Yeah.
said adding 2 to both sides produces equivalent equations. Why is what you're doing there producing equivalent equations? You're adding 5x minus 3y to the left and -2 on the right.
Because the 5x minus 3y equals the negative.
Right, and how do you know that? Where is it in the problem?
Right up there.
It is your second equation, right? Does 5x minus 3y always equal -2? No.
No.
Tomorrow it may not. The next question may not. But for this question right here, 5x minus 3y equals -2. Therefore, you are adding the same thing to both sides, just in a different form. Okay? You know, that's one of the reasons why I like writing things in this horizontal format too. When I grew up, when I went through my algebra classes, we wrote the adding 3 to both sides, we wrote it in a horizontal format. Now, I think personally there's too much of the vertical stuff. Not that the vertical stuff doesn't have its merit, but I think you miss the I'm adding both things to both sides and it's an equation. Like, you don't, if we all know what I mean, right? 2x plus 3 equals 8. Subtract 3 from both sides. Underneath you say -3 minus 3. I see with that visual that I'm subtracting 3 from both sides. What I don't see is that I'm creating the equation, whatever I said, 2x plus 3 minus 3 equals 8 minus 3. That actually shows me the equation that is formed, whereas when you just do the math here and in the vertical format, you're actually showing the result of the equation that's formed, not the equation that's formed, right? So I certainly think there's some merit in going horizontally, you know, instead of, you know, that. But, okay, so yeah, that's good. Okay.
Can I get one with exponents or powers, please?
I know, no, you've already explained that ad nauseum.
Wait, so that means I did 2 questions,
Yeah.
then, right? So skip me.
You wish. All right, let's see what's this one.
Played.
Whatever.
Ready. Rhyme number 2. Oh, prove that invert and multiply for dividing fractions works by getting a common denominator and then dividing straight through.
Invert and multiply, we say.
So now, you could, depending on what you feel comfortable with, you could either take because I just say prove it. If you want to prove it with a specific example, or if you feel really comfortable, you could just prove it with A over B divided by C over D. But if you'd rather, I'd probably say it's a little bit more powerful to show it first with real numbers. So I'll give you a problem, okay? So 3/5 divided by, now I want to be strategic about this because I don't really want to say, well, I guess this one I could say. So I'll say 2/3 divided by 2/3. Now, at first I was thinking, oh, that's not a good example because the 3's cross cancel, but we know we're going to invert multiply, and then the 3's in the numerator. And so I'm looking at that and I'm thinking, okay, nothing's going to cross cancel, because I don't want to do that because then something might mess up in the process. So what I want you to do is this. I want you to prove that invert multiply works. So over on the right, let's invert multiply. Do 3/5 and then, times 3/2, right? And then what do you get? You get 9/10. Okay, we know the answer is 9/10. I want you to show that you will get 3/5 times 2, or 3/5 times 3/2 if you, so we're proving invert multiply works by getting a common denominator on those and then dividing straight through. So get a common denominator on those two fractions and divide straight through. Go ahead.
So what you first want to do is get a common denominator. This does not have to be the least common denominator.
And I strategically picked right that there isn't a least common denominator that isn't the quick common denominator.
However, in this example, the least common denominator is the quick denominator, and the quick denominator is going to be take the 3 times the 5 and the 5 times the 3. However, that doesn't end there because you have to multiply the numerators by that, because what you're doing here is you're multiplying 1 over 1, except 1 over 1 shown as 3 over 3. And you're multiplying 5 over 5, which is still 1, which allows you to do that. So that means you will now get 9 over 15 divided by 10 over 15.
You will have to work on your board writing at some point.
I do, yeah. I really want to work on my board writing. So we get 10 over 15.
I'll tell you what I think your problem is with writing on the board. I think you're standing wrong. So go into and we all need to do this from time to time. We probably don't do this enough because it's just one of those silly things. Just go into a room with a chalkboard, right? I think a lot of people I think write incorrectly with chalk because they hold their chalk like a pencil.
Yes.
Okay, that makes it harder because that's usually where people get the squeaking too, because you're holding it too straight. Now that's fine if you're gonna lean and do it, right? But so most people hold it then like this instead. That way you're writing with the I don't know if it's really called the edge, but the edge instead of writing like a lead of a pencil.
Yeah.
Okay, that's where you usually get the squeak. Now some chalk doesn't squeak, and that's good. But anyway, but then I think that part of your messy is you're also standing like this. So you are standing and having to reach over your body, and that's not how you write on a piece of paper, is it?
No.
You write on a piece of paper by having. You don't put. I highly doubt that if you're writing with your right hand that you put your piece of paper over here. My son that's left-handed does that. You don't write like this. You put it over here and write like this. Okay. So when you're standing at the board, I'll stand like this. That way, my paper is to the right of me, and I am. See, so you're.
So you want me to stand?
Face like me.
Face like you?
Yeah, like that.
Yeah.
And then write like that. That's how you write on up. And for me,
it feels strange.
I know.
It's like I'm
but hold on. But you're not standing like this.
Well,
you're standing at an angle to the board, like you would with a piece of paper. Now you have to also master. You also have to master the art of I'm writing and I'm yes I am turning this way every once in a while. Right? To look at my students.
I want that board now.
So maybe chalkboard writing 101, right?
Thank you.
And for me, when I'm writing chalkboard, I just have to write slower to make mine neater. You know, I write slow because I'm writing fast sometimes when I can write neatly if I, well, I don't know, neatly, I can write legibly, if I just slow down. Okay, so we're at 9:15 by 10:15. He's gonna turn right again. I know, it is that's why you will probably have to just get yourself in a room, lock the door, and practice right for now, let's not mess with
That's in my head now.
your
so
usual stride. Okay, go ahead.
God. Alright, so notice the two 15s in the denominator. What is 15? I'm gonna do it.
Just do it.
I can't.
You have to practice that later. Just do it. Do your
What? 15 divided
Now you
by
know.
15 is 1.
Okay,
And 9
The chalk didn't do anything to you.
keep going.
is 9 over 10. But 9 over 10 divided by 1 is equal to this 9 over 10. And sure enough, these two are equal.
And then if you wanted to, in general, if you did it with A over B and then didn't simplify anything, well, nothing would be able to simplify, right, because A's and B's and C's and D's, then you would get that A over B divided by C over D ends up being the same as A over B times
Do you want me to show the
D over C.
general?
No, that's fine. That's fine.
Okay. I was already defeated enough today.
Yeah.
I was feeling good on that first one.
No, you did fine. Yeah, it's just, it is. Writing on the chalkboard, though, is a different art
I
than
know how to erase in the chalkboard.
other things. That's not an art, that's just do it.
Manual labor.
All right, Ashley. What is a good conceptual definition of the arithmetic average? So I don't want a procedural definition. Arithmetic average is the number that you get when you add them all up and divide by however many the numbers are. But what is a good conceptual definition of the arithmetic average?
It's the number that you put in place of a number without changing the sum.
Okay. The number you said the number that you put in place of a number.
Yeah,
So-
a number that you can put in place of any of the numbers.
Right, of a group of
Yeah,
numbers. Okay, of a set of numbers.
Yeah, without
Okay.
changing the
Without changing the sum of that set of numbers. Okay, all right, good.
That sounds pretty old school.
It is. I think it's from 1902.
sum.
Yeah, and then from there, of course, we can do activities, right? Where you would say, hey, let's take these numbers represented as chips, right? And then move them around to put in place of. But you still have 5 numbers, and you can't add any more chips. So you have to put a number in place, an amount of chips in place of each of the amount of chips that would not change the sum. So, yeah, good.
I'm gonna derive something.
Yes,
You what?
I'm
I'm
getting
getting
all
antsy. I was like, I want to
the
derive something. Like
Oh,
these
man.
ones are all
I keep getting
easy.
like the difficult ones that I know though.
Yeah. I don't know.
What's this one?
Oh.
Cody! Let's see how you might, and I'm not expecting you to really get this complete, but derive the law of cosines.
Oh, okay, good. I know this one too.
That is the harder one, I think, but yeah, let's see where we can go with this one. A little harder.
I never heard that one.
You had it? You had it
It's okay,
now?
I'll-
Well, I mean, we did do it in geometry, too.
You just want me to derive the law of cosine?
Yeah, see where you can go with that. How do you start?
Or do you want?
Can we start by saying the law?
Make your choice.
Well, yeah,
even
you
though I know it.
So let's
Yeah.
write it down first.
So the law of cosines is a squared plus b squared minus 2. Is it a?
Yeah. Just
A
A, B.
cosine.
Right, cosine of the other one.
The big
Yeah,
C.
that's a big C.
Yeah.
That's it.
And that equals what?
That equals c squared.
Right. Now, we know, well, no, I don't want to say that because another question is there's a relationship, right? But we know that it is the relationship in an oblique triangle, right? So a non-right triangle.
Mhm.
So we start out in the derivation with a triangle that is not right. So, and I don't know if it usually takes a little while to kind of, yeah, but, so, yeah, now, I would probably say that's a little too equilateral,
Yeah.
isosceles.
I didn't mean to make. I'll make it.
But yeah, try to start with your left side, and then right, and then make that other one. Yeah, that's probably a little bit better. I mean, it's possible that's a little isosceles, and in fact, even possibly that's all right. No.
No.
Because it's not only isosceles, but that angle at the numerator, the angle at the top could also have been a little bit too right.
There we go.
That's probably pretty good, but at least it wasn't the typical right triangle, right, where we do a vertical and a horizontal. That right angle was up top, and you usually don't kind of see it that way. All right, now here's the key to this, and you don't have to remember how you're going to label your vertices unless you really want to get a squared plus b squared minus 2ab cosine c equals c squared. It's okay if you get a squared plus c squared minus 2ac cosine b, right? Right, so I personally don't worry about where I put them.
Yeah.
And unless you remember something, just get some labels for, no, those are capitals.
Oh yeah.
Vertices are capitals. And then the sides are lowercase, going with them, okay? Now, what do you do to get this law of cosines?
Oh boy, I did not practice this.
Jess knows, doesn't she? Well,
Yeah,
hold on.
I know this one.
Oh, you know what? I should have asked if you want to, I guess if we could, phone a friend, or actually if there was somebody in the class that you wanted to pass to, that said, hey, I can do this, maybe we could pass it. You want to pass it to Jess and you take another one after?
Nah, that's not fair.
Well, if she
already did one.
if she wants to do it.
So,
Okay, well, but Jess at least helped you out and said, drop a what?
No perpendicular.
Okay, yeah, because what we want to do is, the one thing I think about is this. Because I know, I'm actually going to already answer one of the questions. I know that there's a relationship between the law of cosine
I know the relationship.
and the Pythagorean theorem. What I'm going to do when I get, but I also know that the cosine is how to solve an oblique, a non-right triangle. I prove it by getting a right triangle. And so that tells me, drop a perpendicular. Everything else from there, I can get. So when you drop that perpendicular, it does something to the A side.
We're finding this side.
Right, but you're going to use the two right triangles,
Yeah.
so it does something to the A side. Where's the A side?
Oh, it makes this x.
Okay,
This is a minus x.
Okay, so that's x, that's A minus x. Okay, from there then,
So now
start getting some relationships based on Pythagorean theorem. And you might want to say the altitude though, the perpendicular that you did drop, the altitude, you better label it. What do you label it? Okay, H. All right. What are some relationships in here now?
So now we would have the relationships of x squared plus h squared is equal to c squared and a minus x quantity squared plus h squared is equal to b squared.
Okay, where are you going from there now?
So now you can take. Oh, and also, I don't know. Does it matter if we have A? A is,
No, you can just use those two. What's common with those?
The H.
Right? Think about what's common with those, and that H is not in the law of cosines, right?
Yeah.
So you want to get it out of there. So
So,
how can you do that?
well, you would have H squared is equal to C squared
Right,
minus
from the
X
first.
squared
Yeah.
and H
And
squared
right.
is equal to E squared minus A
Right.
minus X.
Right. Now you can do what to those two
And
expressions?
now set those equal.
Okay, then that gets the H out of there.
So now you have C squared minus X squared is equal to B squared
Now just a little bit of algebra, you should be able to do it quickly.
A minus X quantity squared. I lost where I was going.
Well, just
So
simplify.
now C squared is equal to B squared minus A minus X quantity squared plus x squared, and if you write that all out, that's squared minus a squared minus 2ax. Oh, plus x squared plus x squared.
Yeah,
So wait,
squared minus 2.
your minus is messing you up.
Yeah,
Because it's a minus a squared, but then that middle term
Oh, yeah,
is a, no, that was right. Your next term, you're trying to do too much in your head probably. Your middle term of a minus x quantity squared is negative, but the minus changes it, and then the next term, the x squared, is positive, and the minus changes it.
Yeah. So
Okay.
now these cancel out,
Right? And what are you left with?
and you're left with c squared is equal to b squared minus a squared plus 2ax.
So now that's pretty close to your formula up there, right? The law of cosines?
Yeah.
But
Yeah.
what's in there that doesn't need to be in there?
The x.
So we need to look for a relationship with x, probably that has to do with cosine c.
Oh boy.
Wait a second, is that right? X.
Mhm.
Oh, okay, I'm sorry. I thought his c was an a up top there. I got you. Okay.
Yeah, that's.
Yeah, I got it.
So now.
And this to me is the hardest part to remember. But just think, you want cosine c in there. Cosine. Oh wait, but it is cosine big C.
Yeah. Cosine of.
Oh, okay, wait, you know what? I'm sorry. I said something wrong there. He's got c squared. He might have got excited because c squared, but it is c squared equals b squared minus a squared, when you actually don't want c squared, a squared. You want a squared plus b squared. So you're actually not deriving what you initially wrote, which that's what I said is sometimes the difficult
Yeah,
thing.
if you had
Do you understand what I mean? Which is not a bad thing. You just have to understand it. You're not actually deriving this because this solved for c squared has a squared plus b squared. Your solve for c squared is b squared minus a squared. Okay? So if you're going to do it this way here, I suggest getting it solved so you have two things added together, right? Equals the other one. So how could you rearrange that to make it one of them is on the other side, and so think about it. This is minus a squared.
Yeah.
If I put it over there, and then oh wait, is that right? No, I said
No, you're
no,
right.
yeah.
No, because
Yeah.
you're subtracting.
No,
c
that's
squared.
fine, and this needs to be a minus. So it would be what? A squared plus c squared though, right?
Yeah.
So you're gonna move this over and this over,
Yes.
Oh.
right? And that's the thing that I think makes it the hardest, because when you derive it, the tendency is to write it like this, but you have to realize that there are three things that I could derive.
Yeah.
So either be flexible with that if you're doing it on the spot, or what I do is I spend time in my office making sure that I put the right vertices.
Yeah, he just needs to be in a C.
Right, if I put the right vertices in order to form
Then
that right
should
there.
be minus,
So this would be minus, you're bringing that over, so that's a minus.
Alright.
Now that looks like this, only
Except
with
X.
B's and C's changed, right? You have B squared here, this is C squared, you have C squared, this is B squared. So now we can say,
Cosine.
right, so now it's gonna have the cosine to do with this right here. So now, let's maybe come up here, oh, maybe we'll say this, but, and then, I never like to look at X, I mean, I like to look at, well, first of all, the cosine that has it in there, the cosine of B, but the cosine of B equals what? So what is the cosine of B? This angle is what?
Sit over.
Right. Well, wait, no, cosine's adjacent over hypotenuse.
Yeah.
So
Gosh.
x over c, or x equals, right? Just because that's how we think of it. Usually we think of the cosine of the angle. We don't think of this side being that times the cosine of that, which is fine. I mean, we should be able to think of it both ways. All right, so x equals cosine b in yours.
Cosine. Gotcha. C cosine B. So then when we go back,
So now,
we get a squared plus c, is it c squared? Yeah, c squared minus 2ac cosine b equals b squared, which is
one of the three formats.
a different
you did
way
like that.
of,
right.
yeah.
Right. So, you again, you have to be careful. Either I will write all three laws of cosines down,
Yeah.
and then just figure out which one I'm getting. That's usually not the way I do it because I plan well. So, but if somebody just asks me off the spot, then I have to be flexible. If I'm planning it in a lesson, then I write down that I want to drive a squared plus b squared minus 2abc cosine c equals c squared, and I'm going to put my vertices of my triangle in a certain place. So either way. Okay. Yep. I guess one way, if I always think about my triangle being the way he drew it, I never really looked at it this way before, I usually just memorize how I do it. And I know I'm going to put cosine C in. C has to be on the left side, right?
Yeah.
C has to be on the left side. So if he just changes B and C, and A is always at the top for me. So if you put it that way, yeah. Or I guess you could remember A at the top and go clockwise.
Yeah.
Remember
That's
tab.
really easy, yeah.
Yeah, or if you're going to remember that you spell something, yeah. All right, good.
I love them.
Jess, number 3.
Wait.
What?
Oh yeah, I thought for a second I
Oh,
thought we
no,
were going
because-
down like this. And I'm like, huh?
All right.
It's been-
Jessa. Oh my goodness, what are our 3 axioms for teaching?
Lottery winner.
Know your crap, know more than your crap, and teach from the overflow of crap.
Okay, so know what you're teaching, know more than what you're teaching, and then teach from the overflow of that knowledge. Okay, good.
Thank
Okay, you got the one you wanted.
All right.
Finally.
Finally got that. I didn't even plan for that. Ryan.
Oh
The
god.
one that you already explained.
This one's a.
It does have to do with exponents and bases, but it's not the one that you thought, okay?
Okay.
So the actually you can just read this, or you can have it if you need as a reference. But the exponent rule for multiplying like bases says to keep the base and add the exponents. If you do multiply the bases together, what do you have to do with the sum of the exponents? You need it as a reference? So the exponent rule, so I'll help you out here, right? The exponent rule for multiplying like bases says to keep the base and add the exponent. So what I mean is,
An
example, right? 3 squared times 3 to the 5th
times 3 to the 5th
equals 3 to the 5 plus 3 plus 5, 8. That's squared, sorry, okay, 7.
Sorry,
I'm sorry.
7,
I was thinking.
which is also 3 to the 5 plus 2.
Right.
Right.
And now I probably would say this though. Let's put a 3 to the 3rd because I do want my answer. I do want my sum
I
to
see
be
now.
even for a certain reason.
I understand.
Again,
why
this
that
is the planning thing, right? So
Completely.
now the question is, if you did multiply the bases together,
Let's multiply the bases together.
what do you have to do with the sum of the exponents?
Well, 3 to the 5th times 5 to the 5th.
No.
No.
3 to the
3 to the
3rd times
Oh,
3 to the 5th.
Yeah, so what would you have to do? Well, if you multiply the bases together, you would say, oh, it'd be 9 over 8, but clearly that's not that. But what you could do is you're like, oh, 3 to the 8 is also, you could write that out again as 3 times 8, pretend there are 8 3s here, okay? And you're saying, oh look, but these 3s group up to 1 9, and your other 6 invisible 3s group up to 3 9s. So this is no longer 3 to the 3rd times power x. Dang it, I
Just
said
3 to
it.
the 3rd. 3 to the 3rd is
3 to
fine.
the 3rd times 3 to the
Or
5th.
the 3rd power of 3.
The 3rd
The
power.
5th power of 3. The first one is the 3rd power of 3, and the second one's the 5th power.
Okay, okay.
Because you're looking at this whole thing. That's all.
Yeah, okay, I see.
I get you.
So it wouldn't be 9 to the 8th, but it would be 9 to the 8th, 8 over 2, which is equal to 9 to the 4. What does this mean? Well, if you multiply the bases together, you would have to divide your exponent by 2. And I also erased part of my 9. Do you want me to show that for the general?
No, I think that's good. Good, alright.
For a second, whenever I saw that one, I thought it was the quadratic formula because it was like so much thicker than the other ones. Advantage of being next to Steve is
Well, derived quadratic formula would just be really small. Alright, hold on, I got 2 here.
What? The daily double.
Alright. Ashley. Oh man, how are the Pythagorean theorem and the log cosines
Can I
related?
more challenge?
Oh, you want more challenging one? Okay.
Yeah. I'm making it a little easier.
I'm just gonna throw that one away because we know.
Yeah.
What?
We
It's
can't
not
answer that
I
one.
will
Theorem
remind
is a
the
special
judge.
case.
I wanted. Okay, that's a good one. How or what is the pattern to show students for why the product of 2 negative numbers is a positive number?
Alright. So, let's just say, here I'll show you. We'll do 4 times negative 3, and that equals negative 12. And then we want to decrease this number by 1, so we do 3 times negative 3, and that equals negative 9. And then also we'll do 2 times negative 3, which equals negative 6. And then 1 times negative 3, which equals negative 3. And then 0 times negative 3, and then that equals 0. And then we'll do negative 1 times negative 3, which equals 3. Now the relationship between these numbers on the side here, the values, this you'd be adding 3, then this you'd be adding 3, and the difference between this you'd be adding 3 also. And then you still be adding 3, and then adding 3. So there really isn't a difference. This is a constant difference. And then also with this side, you're just decreasing by 1. So you're making the same changes, but that's how you get a negative times a negative to be positive.
Okay. I would probably say that with both yours and the way Ryan did it, it's probably more powerful if you hold off on. You guys are both looking at the whole finished product. Remember how we don't? We try not to look at the finished product. We try to be able to have our students play a little bit with math. Both of you looked at the entire pattern as a finished product. What I mean is, you went to your pattern and then you actually wrote down what we wanted the answer to be.
So I should have left
You
this out,
you wrote down negative 1 times negative 3 equals 3. Don't write those last lines down at all.
Yeah.
Talk about what you're seeing in this pattern first, right?
Yeah.
You see that you're decreasing this left side by 1 and it's increasing this by 3. That pattern makes sense. If that pattern was to hold, then the next step in the game is negative 1 times negative 3. The next step in the game is 3 to the 0 equals what?
Oh, I didn't do that? I'm sorry.
No, you actually wrote as you were writing the pattern because you were thinking about the
I
pattern.
thought I went to 3 for the first.
You wrote 3 to, no, you ended up writing the 3 to 0 is 1, and then you showed, like she did, divide by 3, divide by 3, divide by 3. You showed plus 3, plus 3. Leave that last line, and then say, well, if that pattern is going to continue, what would negative 1 times negative 3? So you were kind of answering the question. Let's think about the difference there. You were actually showing, let's see, how can I say that?
I was showing the pattern.
Oh yeah, but what I'm thinking
I
is,
didn't like leave like you know.
what I'm thinking is you guys probably presented why the pattern shows why a to 0 is 1 and negative times negative is positive. You probably didn't use the pattern to show why it makes sense that it is. You see the difference there? Like I can present something, but if I'm going to show that it makes sense, it's more of an inquiry. Like, why is this? Look at the next step. Look at the pattern. You know, kind of things like that. And so we want our students to be able to make the leap themselves instead of seeing the leap by reading the finished product. You know, more than anything else. So
Yeah.
All right, good. This will be the last set here. We'll stop that. Coded. Oh my goodness. Karoti is deriving the quadratic formulas. Do you want to do it?
Good job, Karoti.
Oh man.
I remember.
Start us out.
So
What do you do?
a general quadratic.
In general, we should be able to answer this though. Just not rather than derive it, let's answer this question too. How is it derived? Give me a phrase. Like, how is it derived? We do what to the what? If we're gonna, when we do something, what's the process we use? Starts with a C.
Complete square.
We complete the square on the what?
On the general quadratic.
On the general quadratic equation. That's the way to look at it. We do a process of completing the square on the general quadratic. Now we won't stick you with all the nasty algebra, but
that's
at
what I was
least,
gonna do.
well, no, but I mean at least start us out. Yeah, I mean when it gets really bad.
Yeah. So.
What's the first step?
X squared plus bx equals negative c. Oh darn it! I forget how to. Take an x out.
No, we're not taking the X out.
Oh no, that's what we did, Cody. Like we did it completely wrong.
There is something, the reason I want you to at least start us out is because your first step is fine, but there is a very, very important next step if we're going to use the process of completing the square that I want everybody to make sure they have to do. What is it?
You have to add.
Now, before that, and it's the thing that I can say that I often forget myself if I haven't derived the quadratic formula for 5 years. You know, if I've had a dry spell where I haven't taught algebra and quadratic equations and I haven't derived it, sometimes I forget this step and I start doing what he did. I move the C, which that's fine, but then he says, well, I need to take half of the B and square it, but you're missing one crucial step that we cannot miss. Something's wrong in front of x squared.
Oh,
What?
a can't be 0? Or,
Well,
well, I mean, that's true.
A can't be 0, that's true.
Very nice.
But it also, it's not that A has to be this, but the thing in front of x squared has to be what?
1.
Has to be 1. Now it's possible that A is 1, but it's possible A isn't.
Yeah.
But one way to make sure that the thing in front of x squared is 1 is to do what? To both sides of the equation.
Divide by a.
Yeah. So when I divide by A, both sides of the equation, right? And you could have done this first, but it really doesn't matter.
Yeah.
You get x squared.
It's coming back.
Now you're getting it. Right, over, right. Okay. Now I do want you to do the, what do I add to both sides to complete the square on the left side?
It'd be half of b over a.
What? Not just half of b over a. Half of b over a what? How do you complete the square?
Oh. Yeah, half of b over a divided by 2.
And then do what to it? That's just half of b over a. You don't add half of b over a to both sides. You add the what of half of b over a?
Oh, the square root?
Not the square root.
Wait,
The-
what?
Wait, go to an actual problem then, because you're missing something. X squared, write down x squared plus 6x, and we'll just leave it at that, okay? Now, if you want to add something, what do you don't add 3.
Oh, you're right. Yeah.
You add-
yeah,
You divide by 2, and then you do what?
Well, I need to write the answer out. Oh my gosh.
It will be, put it this way, it will be x plus 3 quantity squared. So put x plus, right now, put x plus 3, and then quantity squared. That means 2x squared plus 6x, what are you adding?
Half of this? Wait, what?
What would your triangle?
Well, it'd be this square.
Yeah!
I was. Okay, yeah.
Yeah, you're gonna add 9.
I was skipping that part.
Yeah, so you're not adding, we know what I'm trying to say. You're not adding half of b over a, you're adding,
Half of b over a squared.
right, okay.
I was totally skipping that part. So
To his credit, he probably got through the hardest one, the actual drawing. But,
Yeah.
b over 2a, so b
he tried those the hardest, right? So b over 2a squared
b
is what?
squared over 4 squared.
Right. Equals what?
Negative c over a.
Right, careful. Negative c over a what?
Oh.
Yes. You need to go practice this, right? You add that to both sides. Okay, now we will stop at the next step on the left-hand side there. What does that look like then?
X plus b over a.
Not b over a. It's half of that, so it's b over 2a, right? Because there's going to be two of them.
Yep.
Squared, right? And then we won't do the rest of the out. But if you combined like terms there, or not combined like terms, if you got a common denominator, you would start to see the quadratic formula forming. And then if you took the square root of both sides, you use square root property, then you solve for x and you get the quadratic formula. So we won't finish that up. Okay, good.
Sure.
Yeah. That's just a matter of practicing the algebra. All right, Jess. What's Jess gonna get? Jess gonna get this one. This
I don't remember
one.
what other questions were.
This one says.
Says.
If S-A-Y is say, why doesn't S-A-Y have says? Makes perfect sense.
Okay, I couldn't answer that one.
How are the terms exponent and power technically different? 99 didn't really.
Why?
Even though we often use them as synonyms.
The
And if you need to show as an example, that's fine. But what?
The power is the product. Hold on, I'll just write something. So if we have like 2 squared equals 4, your 2.
Wait, I'm going to stop you right there and never show 2 squared, 2 times 2 as like a first example in that. Yeah, do something.
I was just thinking something
you get
really-
you get 2
3
2's in
squared.
there, and you're
2
trying to
plus 2
distinguish.
2 times
Right,
2.
you try to distinguish which one's the base, which one's the exponent. Well, 2's the base, 2's the exponent. Okay, I like that. 3 squared. Okay.
Thanks, Ashley.
No.
Okay. So the power is, well, I guess you could say, isn't it 3 squared like as the whole, and it would also be 9?
Okay, yeah, the power is actually
It's the same.
right. The product, right?
The
P
product
and P.
of-
So it's whatever 3 squared is the whole power, which is 9 simplified.
Yeah.
Right.
Okay.
The whole thing's a power.
And then the exponent is the 2 because that is how many times you're multiplying the factor.
The exponent,
3,
right?
yeah.
Yeah, the exponent. Yeah. So the exponent is 2, but the power is actually 9, even though we often use them interchangeably. All right, last one. Bring us home. What does he get? What does he get? Oh man, they're all.
This one's gonna be the why isn't it says?
Well, you can't get quadratic formula, right?
I know.
Why does cross multiplying work when solving proportions?
I love this one because I found this one out of myself.
Okay, all right, well there you go. Why does cross multiplying work when solving proportions?
You want me to do the general?
Well, you know, this one here, you say general though. No, I wouldn't say A over B equals C over D, but put an X somewhere. You know, like 2 over 3 equals
2X,
X over 5,
yeah.
something like that.
3x.
Yeah, I don't know. I wouldn't
7.
necessarily do.
Not 3, just
Do 3
X.
7
Well,
equals x over.
Okay.
Yeah.
Can I write 3x or
You
just
can
X?
write 3X because you're still solving for X.
Yeah.
Yeah, we can see where it goes. 3x equals 7, or 7 equals
4
any number you want.
Nah.
Yeah, probably
I'd say
something that
3.
doesn't simplify, right?
13.
Yeah.
Let's do a prime number. Alright, well, what you're really doing whenever you cross multiply here is you're really finding the quick denominator and not the least common denominator. Very similar to the other one I had too. So what we're doing here is multiplying both sides again by multiplying the numerator and denominator divided by 4. Denominator, numerator by 7, which is also, these are both 1, so you can do, I mean, you could do it too if it was like 8, as long as these both were the same side, because this is an equivalence equation, so as long as you do the same exact thing to the one side to the other, it's legal. But this is also 1, so. Anyhow, moving forward, so 4 times 3x, we could say is 12x over 28 equals 13 times 7. Oh boy, I don't have my calculator.
91.
130 divided by 2 is
91.
65. 65 plus 26, 71, yeah.
That's a
Thank
weird
you,
way of doing it.
Yeah.
Wait, how did you do that now?
You did.
I
Yeah.
enjoy hearing how other people do it. 'Cause
This
my
is
son
what
does it.
working on homework with him.
All right.
But you said 130 times.
Mental
You
math.
said half. So you said 130. You did half, which is 5, and then you just added it 2 more times for 26.
Yeah.
That's good.
Mental,
something my son
mental
would
math
do.
techniques. 2, 3 are easy ones.
Yeah.
5 and 10 are also easy ones. You
Yeah.
can derive the rest from just using any
Right.
of the others.
I wish I would have learned
I
more
learned that
mental stuff. In the
Yeah.
70s when I went through, it was not mental math.
I did not
Remember, it was
learn
back
that
to the
from class.
basics.
I
so
learned
all
that
we
for
did-
myself, just like learning
Well,
patterns.
my son does. I mean, my son would also do that by 21 plus 70.
That's what I do.
You know, and that's how normal people would do it.
Listen, this is what, like, when we're doing homework, he'll do something and like it sounds so strange.
But I
to me, and
appreciate
make him
that, but-
Stop and I'm like,
Yeah, but I appreciate that thinking because knowing how other people think,
Yeah.
it helps us as teachers because when a student does some, different way than us, rather than saying, well, why don't you just think of it as 7 times 3 and 7 times 10, that is a little too algorithmic, right? When that way is very, very mental, mentally correct, or mentally
Because
stimulating. I guess.
multiplying by 10 just adding a 0. No?
Right, yeah. Okay, all right, go ahead though.
All right. So we have 12x over 28 equals 91 over 28. Notice how both of these denominators are 28. These are equal denominators, so therefore we could say as well 12x equals 91, where we simply multiply both sides of the equation by 28. So that way, again, these are equivalence equations, so you're canceling out the denominator because you're multiplying both sides by 28, which you get 12x equals 91. Now look back to here. Whenever you cross multiply, which this horrible algorithm, which we should never do as teachers, it says, oh, just cross multiply, and that's 3x times 4, that's 12x. 13 times 7, that's 91. Well, they're both the same. Cross multiplying works. But you should never say that to class.
yes, you should.
So,
But it's not the
So
only
looking at that before he erases that though, there is a little bit of danger in what he did in the sense that, remember this, there are multiple ways to get 12 and 91 with multiplying various things. Since there are, that doesn't necessarily mean that the cross multiplying works. What would have been more powerful is if he would have not written 4 times 3x is 12x. If he would have just left it as 4 times 3x. And the 91 left it as 13 times 7. You see what I mean?
Yeah.
Because that way you can actually see that is where those numbers are the same. In fact, I ran. Oh man, I'm not going to remember. But I ran.
So
you can erase-
basically, what I should do is add a step then where it's 4 times.
Yeah, right.
3x.
Just 4 times 3x.
4 quantity parentheses.
Right. I ran
3x,
it.
and-
What was I reading?
Yeah, that makes sense.
I was reading a book, or was it something that I actually did? And it was weird that it came out to be the same. Man, I can't remember what I was doing there. I feel like I was just reading something. And the products and the sums were the same, but it wasn't actually how you got it. And I was like, that's weird because you don't get it, but it was, oh, you know what? It was somebody's history of math final. They did, I'm not going to remember the numbers right offhand.
Does it work? in
80
general?
times 3 is 240, right? No, this couldn't have been right though, because 63 times, wait,
Yeah, like
what were my numbers?
4,
Because that's 4 something.
6 times
No,
8
it's
is
504.
Well, yeah,
Yeah,
but I
it's
mean, it's
4
more
equals-
than, more than that.
Oh,
What
yeah.
the heck was that?
Does it need
Oh
to
wait,
be
no,
before
what?
that?
6. How about this? So wait, that
480.
83. Let me try this one. What's 83 times 6? So 480. Yeah, that's 504, right?
Yep. No. Yes.
Because it's 480 and 24.
20. Yeah. No.
504?
480.
like 18, yeah.
Wait, say that again?
480.
Oh, and 18.
Yeah.
Okay, hold on.
Okay, Steve and I are in the same boat here.
Yeah, well, I was thinking the 504, right? So that ends up being, wait, that's only 490. So, and then what was the other one?
But that one is
But this one
504.
is 504, so hold on. 60, was it 60? Oh, you know what? No, 60.
62? No. This is-
60.
But those are
So
all
that's
nice.
480. Ah, dang it. Anyway, whatever my numbers were, I was asking them to solve a multiplication problem by the doubling. Was that right? That one was, oh well, by doubling, but this was, I was actually doing it by Napier's rods, and so that's kind of like the lattice method that we teach students today. But anyway, whatever the numbers were, it ended up being that 83 times the number was the same as 60 times a number, but the work was actually really different. The thinking about the problem was different. The concept was different. It just happened to be that the numbers came out to be the same. It's kind of like saying, whatever, here the best example is saying that, those two are, you have to be careful with this in a proof kind of a situation.
84
Because
times
those are the same, was it 84?
Yeah, 84 times 6 is 504.
Oh yeah, then that's 504. So somehow the argument though,
No, that would be 63.
that these were 63?
Yeah.
Well, I don't know, whatever.
No. The 60 would be 63.
Oh, and then that's 63.
Yeah,
Okay, I
then
gotcha.
you're good now.
I gotcha. Yeah, so whatever the numbers were. But anyway, the point is that just because two numbers come out to be the product of two different numbers come out to be the same, doesn't mean that conceptually it was the same problem, right? So what I mean is that's like saying 4 times 3 is 12 and 6 times 2 is 12, yes, but neither one of these are the same. So depending on what your problem is, it's like is 4 times 3 representing 4 legs of 3 cats or 3 legs of 4 cats? So the point is you have to be careful with that. So when you just look up there and say 12x equals 91, yes, the cross products are 12x and 91, but how do you know without that middle step that 12 wasn't obtained some other way and 91 wasn't obtained by another way, and that it actually comes from the cross product, and you don't know that if you don't hold that.
Showing it the 3x times 4 was 12x.
Right.
Yeah.
Well, the ones you didn't get to were, what is the square root of x squared? And we know that that's actually the square root of x, right? And what does the phrase pedagogical content knowledge mean to you? I mean, what does that mean if I said pedagogical content knowledge? So there's pedagogy and content in that phrase. How would you answer that? What does it really mean? It's not just pedagogical. Pedagogy is just the way of teaching things, right? It could be very general. Content knowledge is math, but pedagogical content knowledge, put them together, is really methods of teaching specific things, right? So, and then the other one was, what does it mean? And we kind of answered this with the common second difference thing. Was, what does it mean when we say that the slope of y equals 3/4 x minus 5 is the number 3/4? saying it this way means we can't separate the number 3/4 into the 3 and the 4, and so we can't speak of up 3 and over 4. Remember, it's 3/4, so when the independent variable changes by 1, kind of Cody's 1, 1, 1, 1, the dependent variable goes, in this case, up by 3/4, right? Changes by 3/4. So good. All right, well, no, you guys did a nice
I
job
thought there was a
answering
writing
those.
portion too.
What's that?
I thought there'd be a writing portion.
Yeah, that's what
Oh.
I thought.
That's what you told us.
Yeah.
Oh, writing? Oh, you mean,
For
oh, well,
deriving the.
oh, for deriving, yeah, well. you know.
Oh,
Yeah,
I thought we were.
I would
all
probably
gonna do,
say
like,
this.
a little short test and then go.
No, I
You're
like
welcome,
these.
class.
No, this was a good class. You guys really did work hard. Honestly, after answering these, you guys did well. The harder ones I expect people to struggle with. You know, right now, you'll get better at refining. You know, I'm prepared to give everybody an A, you know, in here, so I don't really see any distinction between, you know, A's and A minuses. And some of you had to work harder in order to, you know, get to the intuitive level that some other people, you know, have. That doesn't mean that you deserve an A minus. You know, you work equally hard, and I think you're able to answer them, you know, equally well. So good job. Summertime, you'll hear from me. You know, reading. Don't do anything for a couple weeks, but you know, you'll.
Yeah, it's really, that 504, it's actually kind of, like normally when you do like 6 times 8, like you're thinking of it like how to get 2 different ways to get like 48, right?
Right.
But that was actually like 2 different ways to get 480 and